anyway, you guys are here, so we'll just start learning. Well, anyway, OPAMP, stands for mathematical operational amplifier. That's where that's what they mean by operation, is mathematical operational amplifiers. And yeah, they used to actually be made out of well, I probably can't draw it very well, but tubes, which could have even had 5 pins, and operated on 300-volt power supplies. Now, yeah, they're based on transistors and maybe we can get 1 volt. I think in this day and age of microcontrollers, right, which are digital, right, and yep, can be really fun because you can do so much. People might say, why teach op amps, right? Because with a microcontroller, you can have an analog to digital converter. It's right in the microcontroller. Then once you're there, you can process all your digital logic, right? And then you can even have a D to A to do it back out there. Now, the thing is all of these things require filters, and somewhere in these filters, there's going to be op amps. All right. So, that's there, right? Now, that being said, and these are like, the op amps that you could use in lab, you buy it, but you can integrate, there's chips, right, that have, many, many op amps, or actually something that behaves like a neuron. And there was a guy who predicted that we would have to do this, Carver, and that rather than a bunch of digital chips, we would have a bunch of analog circuitry that actually act like a neuron on a chip, right? And the neurons that I use in my research are based on an integrator. And there's more than one way to do an integrator, and a reset circuit, and just multiply, right? Which all depend upon some kind of op amps. So rather than make it out of discrete parts and put it on a PCB board, you could form integrated parts that then are connected, by those neuron connectors, dendrites, and all that good stuff. All right. So in fact, yep, that's my research area, or one of them right now. All right. So, but the thing is that in a solution, right, analog, right, it's supposed to be faster, lower power, right, where digital, easy to make, easier to make, tolerant to noise. Right, at any given technology node, the analog should be able to go faster, process more things, but it is sensitive to noise, and they're hard to, I mean, yeah, it takes a little bit of more understanding to do an analog circuit, where with digital, they're easier to make, they're tolerant to noise, all right? But, so when they were simulating the moon launch, right, there was an analog computer that would run in real time, but to verify that it worked, it would take weeks. They would use a digital circuit. And the thing is it's really not one or the other. The best things are all going to be mixed signal, where you take and use the advantages of each one appropriately. All right. Now, of course, in order to understand that, we have to understand how the OPAMP works, or at least, and really just from a mathematical standpoint. All right. So I tend to always draw the OPAMPs like this, and then some things about an ideal op-amp, right? There's open loop gain, and that is supposed to be infinite. And I'll go into what each one is right now. I'm just listing them. So another thing is Rn is equal to infinity, which means I minus equals I plus equals 0. So I'm just going to put that here. That's I minus. This is I plus. So if between these two pins is infinite resistance, or it's infinite resistance in, no current can flow, right? These are the ones that are used most often, right? But then there's another one, is that V out can be plus or minus infinity. In reality, you're limited by the power supply. So if that's plus 15 volts, it can't go any higher than plus 15, right? If this is minus 15 volts, the signal output can't go any lower than that. A lot of times in the labs that you've taken, we've designed all the experiments to make sure you never run into any of these problems. But when you're doing something on your own, you could have a signal that gets warped by the fact that it can't go beyond the power supply. All right. And then there's something else. I out can be infinity, meaning no matter what kind of resistor or capacitor I put there, it can push and pull all as much current as it wants. It's not true, right? And then the thing is the gain, go away. No, I don't. The gain is constant with frequency. Now there's some other things, right? So in EE98, right, we did open loop gain is infinity. In 98, we did this here. And you know, 90, 98, it was that. Now in 97, you might have run into where that's not true. And in 98, we did gain it as constant with F. So the thing is we're going to find that, no, that's not all true. And when we start taking away in 110, we're actually going to work on with op-amps where the gain isn't constant with a frequency. But here's the trick is you can choose to design such that op-amp effectively is ideal. So yeah, if I have an output current, if I put a 10 ohm resistor here, most op amps can't handle that. But if I don't put a 10 ohm resistance, well, then it's behaving ideally. If I keep my frequency below where the frequency starts to drop off, well, then it's behaving like open loop gain is infinite. If when I make a circuit has a gain and it's a lot less than the finite open loop gain, it doesn't matter. The op amp acts very ideally. So the thing is the ideal op amp is a model and it's a prediction, but it's also an achievable goal by what you select. All right. Now what I want to do first though is actually op amps can be used as comparators. All right. Oops. And I'm just going to call this V minus and V plus and V out. Now in this configuration, there is an equation for V out, and it's called open loop gain V plus, right? Now it's true, we give this a constant, but many times we set it equal to infinity, all right? So here's the thing, if V minus is less than V out, V plus, right? V out is going to go towards infinity or plus VDD, right? Because if V minus is less than this is going to be a positive number. Positive number times infinity is positive infinity. We can't really go to infinity, right? We just go to the positive power supply. And if V minus is greater than V plus, V out would go towards negative infinity or minus VDD. And so this is a comparator, right? And how might this be used? So let's say I set up a reference voltage. This is 5 volts. These two R's are equal to each other. So it's 2.5 volts. Okay. So let's say we have a temperature sensor. All right, 0 degrees equals 0 volts, and 100 degrees Celsius will equal 10 volts. Well, when this voltage is below 2.5, right? When the temp sensor is less than 2.5, V out equals minus VDD, all right? When the temperature sensor is greater than 2.5, V out equals plus VDD, all right? So, I can change this reference voltage to be equivalent to 30 degrees Celsius or 40 degrees Celsius or 38 degrees Celsius. That temperature sensor could go on a human, and if you have a fever, right, the temperature rises beyond this reference, this goes on to positive VDD, and an LED turns on, right? So it's just doesn't tell you the temperature, but it tells you that it's exceeded, right? It can tell you if so take any sensor that converts something to a voltage, and you can set a trip point with a comparator, all right? And there is a misconception, right? And let's just rewrite this equation again. V out equals the open loop gain, V plus minus V minus, right? If these two are equal, well, then you would have 0 times infinity, V out would equal 0, right? So in general, V plus and V minus are never equal, but they can be super, super close, okay? But there's something, like in the books, well, I'm going to do a little side here, and I guess an aside will be in orange. All right. So if I have a battery and I have a resistor, right? R over R, put that 2, put that 1, right? V2 equals R plus R, V1, right? And there's a current that flows. But what if we set this resistance to infinity, it's like it's not there, right? So if I define the current direction and voltage drop like that, but I equals 0, that means VR, I times R equals 0, and that means V1 equals V2, right? You get that battery voltage. So because the current is 0, there's no voltage drop, that means these two nodes are the same, right? Well, unfortunately, what the textbooks say, despite I tell them they're wrong, all right? They say there's an RN here, okay? And then they say that Rn is infinity, right? That means I times Rn equals 0, which then means V plus equals V minus. But this doesn't work. And the thing is I use the fact that it doesn't work up here, right? This is at 2.5 volts. This was at the temperature sensor volts. and then V out equal the open loop gain times the difference, right? So over here, though, we had R was an infinity, but there was no current, so there was no voltage drop, so node 1 and node 2 are the same. Well, the thing is in this case, there's an input here and no input there, right? Input, no input. So that input makes that happen. But over here, it's an input voltage. This is an input voltage. Well, just think about it. I have a battery, and let's say it's at 9 volts, and I have a battery over here, and let's say it's 3. Well, just because I connect them through an with an infinite resistor doesn't make the 9-volt battery become 3 and the 3 become 9. It just defies any logical sense. Okay? Now, here's the thing. We're going to do an analysis that does show, for some conditions, V plus is approximately equal to V minus. But just saying, here's an op-amp, and it's ideal, and it's an Rn is infinite, it's not enough. Because I can put two inputs here, 1 and 2, that aren't going to be the same. All right. Now, that might be a subtle thing, but I think it's worth knowing. Now, what I'm going to do is I want to derive the non-inverting op-amp, the inverting op-amp, using nodal analysis, even though that's not the only way you have to do it, or you can do it. All right. But it's always good to have a review. All right. So I'm nodal analysis. I guess and I'm going to actually do the current directions maybe in a non-intuitive way. All right. But the current direction is from left to right. So the voltage drop is from left to right. Current direction from right to left. Voltage drop from right to left. All right. Now, at node X, right, write your KCL. All right, so I have IR1 coming into the node, so I'll just put that there. IR2 is coming into the node. Even though these are in opposite directions, right, it's into the node and out of the node, right? So I need to put IR1, IR2 coming in. And then I have I minus coming out of the node. So then that equals I minus. All right, so ideal op-amp, Rn equals infinity, which leads to I minus equals to 0. So now we have IR1 plus IR2 equals 0. All right, that's how we get rid of that. And so many times, this becomes second nature that we'll even forget that there's a current when you're doing the nodal analysis that is set to 0. We just don't even bother writing it at some point. All right, so what is IR1? IR1 is Vn minus Vx divided by R1, right? Plus Vn minus the Vx. Now again, look at where the pluses and the minuses are for IR2. It's V out minus Vx R2. Now you might say, hey, there's a nodal analysis here, and I have one node, and I have another node, but here's the thing. V out is a behavioral voltage source, so you don't need a nodal equation here. You just need to know what is your behavioral voltage source. All right. Now, oops. So what does V out equal? V out equals the open loop gain. V plus, well, it's connected to ground, right? So it's 0. Minus V minus, well, that happens to be Vx. Okay. So V out in these conditions, right, is minus AV Vx. All right. Now, we have a choice here. Ultimately, we want V out versus V in. And so we're trying to eliminate Vx. But we're going to come up with a relationship that it's actually better to solve for Vx. And then you kind of know what Vx is all the time. And let's just do that. So we're going to substitute V out into this equation. So I'm just spreading out the equation. So minus Vx over R1 plus, minus AV Vx R2 minus Vx R2 equals 0. Alrighty. I'm going to say Vn over R1 equals Vx 1 over R1 plus a V over R2 plus 1 over R2. Okay. I want to solve for Vx, so I'm just going to have Vx equals Vn divided by, well, that should be 1, right? 1 divided by R1 plus AV R2 plus 1 over R2. Now, if I gave you a number for open loop gain, 10, 100, 1,000, million, you could plug this in and come up with a value for that Vx, all right? Because V out equals AV, V plus minus V minus, which happened to be Vx. So if I told you the open loop gain is 1,000, and then you knew all these resistor values, and you knew what Vin was, that would be your Vx. This would be 0 in that configuration. Then you multiply it through AV, and you would actually calculate an accurate value for V out. But we're using the ideal op-amp, so that means the open loop gain is going to go to infinity. Well, when AV over R2 is bigger than the sum of these two things, they're going to drop out. But then notice, as AV gets larger and larger and goes to infinity, we're going to be getting Vn divided by infinity. And so Vx is going to be equal to 0. And that means V plus equals Vx equals 0, meaning V plus equals V minus when you have feedback and when your open loop gain is equal to infinity. All right, so let's just kind of summarize. All right, there's no feedback here. I have inputs and I have an output, but there's no way to get the current, like the voltage here isn't fed back onto either one of these nodes. All right, so it's totally independent, and you just use this equation. All right, and most certainly those two things aren't equal to each other. When we started off our derivation, we did not assume these two things were equal to each other. But now with an ideal op amp, this node and this node, right, Rn is 0, so there's no current, there's no voltage drop between the two, and there's feedback, and the open loop gain is infinity. That makes this equal to this equal to 0. So this is the thing to remember. When you have feedback and the open loop gain is infinity and Rn equals to infinity, V plus will equal V minus. Sometimes people think, oh, Vx always equals 0. Not true. In this case it is, but the important thing is that these two voltages are equal under these conditions. Well, now we have this relationship, right? V plus equals V minus when there's feedback, right? And that can be a resistor, a capacitor, an inductor, and even a transistor, a diode, right? There's all ways to feedback, all right? We have feedback, and the open loop gain is equal to infinity, and Rn is equal to infinity. When all that's true, and I'm just going to put negative feedback, then we can say that. So let's rewrite our nodal equation. IR1 plus IR2 equals 0. Vin minus Vx R1 plus V out minus Vx divided by R2 equals 0. Now we can use this relationship, right? Because R2 provides the feedback, right? And I said open loop gain equals infinity and Rn equals infinity, right? So now V plus equals V minus equals Vx equals 0. Well, now 0, 0, V in over R1 plus V out over R2 equals 0 will lead to V out equals minus R2 R1 V in, which is probably something you have memorized by now. So how should you do a problem? I showed you nodal with AV going to infinity, right? I showed you nodal with V plus equaled V minus because AV equaled infinity, negative feedback, are n equal to infinity, right? The other way is you remember minus R2 over R1. I mean, if you did it so many times, right, you would know what it is, all right? But how would you do the problem? Well, in 98, when I wanted to test whether you knew nodal analysis and you could do this thing, I wrote a question. Using nodal analysis, and it was obvious. But then when you started working with more complicated circuits, no, you kind of use nodal with this, right? You noticed the open loop gain was infinity, you saw the negative feedback, you saw this, and then you stated this, then wrote the nodal, and it went a lot smoother. All right. So I'm gonna highlight this, right, and call it like maybe exams and new things, right? But the remembering, well, that might be better for job interviews and higher level problems. All right. Yeah, and when you're doing circuit and circuit design. Yeah, good point. So let's see how this plays out. All right, you see so you see this circuit, and on the 101, I don't think I asked you this circuit. It's too simple. Okay. But I just thought of a good 101 question is how many node equations do we need, right? Well, that's an input and that's a reference voltage. This is to reference, so we don't need that. Nothing connected here, so we need something at Vx. And then there's another node here, but then you remember it's a behavioral voltage source. So yeah, if you had, A1, B2, C3, I think I make 5, right? Right, there's really only one nodal equation. But maybe a lot of people would say 2 because they'd think V out was a node, but no, it's a behavioral voltage node. And some might say 3 because there's V in, and some might say 4 because there's that, and then 5 would be right out. All right. So OPAMP is ideal. We want V out as a function of V in. So we have our choices. Nodal with V out equals AV, V plus minus V in. Prove V plus is very close to V in. Finish, right? We have 2 nodal with V plus equals V minus equals 0. Because we recognize the op-amp is ideal and the feedback, and then we finish, right? And then we have 3, remember, all right? So here's the thing. If you do the nodal analysis method 1 on this one, right? And then you do the nodal analysis on this one, and then you multiply the 2 gains together, right? Well, that's going to take forever, right? And then here it is you're letting the open loop gain go to infinity, proving that these 2 things are equal. Well, then you don't really have to do it over there either, right? But still, this method will take you a long time, and chances are you probably would mess it up. Now, what if you totally forget your whole life because you're in a panic mode? Oh, well, then do that. And then, oh yeah, that's right. These 2 are equal and it's equal to 0, and then you move on. But if you remember, right, that, and we do need a node here, right? V2 equals minus R2 over R1 Vn, and V out equals minus R4 R2 V2. Well, then V out equals minus R2 R1 R4 R3, excuse me, minus. Right? So it really helps to remember the basic gain stages, right? And yeah, what's the other basic gain stage? Non-inverting. Okay. So yeah, let's highlight this method. Alrighty. So what I guess I'm saying is you probably really want to memorize these 2 stages, because I can start adding inputs here and there, and at the end of the day, you can still remember what the gain stage is. All right. So if you know these cold, I can add little bits of knowledge to them to quite complicated circuits. All right. Now, let's say Let's say we have a circuit you haven't seen before. And it's like, wow, what's going on there? Well, there's two things. Is that if you use the impedance, right, ZL equals SL, ZC equals 1 over SC, and ZR just equals R, right? You can rapidly come up with what's going on, right? Just by remembering, like, wait, if it was R2, if it was minus R2 over R1, hey, V out over V in is just going to be ZR divided by ZL, right? ZR is R. The impedance of an inductor is SL, right? And the beauty of that is I can take the Laplace transform, inverse Laplace transform of that, and that gives me, oh, there's a minus sign here, minus RL, integrate V N dt. So the impedance method here allowed me to remember what was going on. And then, yeah, there's certain inverse Laplace transforms you probably want to have memorized, all right? If you weren't going to do that, because I don't, we don't give a Laplace transform table on the 101, right? That's, well, we don't give you anything. So I look at this, and I just don't know what to do with it because what? VL equals L di dt. How do I turn that into a resistance, right? It's a differential equation, right? Okay, well, let's figure it out. Now I'm going to do it more traditionally, where we have the current going this way, voltage drop, current going that way, voltage drop, I equals 0. And yeah, it's going to be IL equals IR, right? But then, ideal R provides negative feedback, right? V plus equals V minus equals 0, right? So if I give this a label Vx, right, it's equal to 0. Okay. Let's see, how's this going to work? So IL equals V in minus Vx, right? Divided by what? I don't know. I have to figure that out. Vx minus V out R. So that's good. That's good. And in fact, right, we can get rid of that already. And we can get rid of that already. Well, I know what VL is. Okay. In this case, because Vn minus Vx equals VL, Vx equals 0, that means Vn equals VL. So we know what Vn is, right? And we can write another equation now. So Vn equals the inductance di dt, right? And that's DIL. So what's the best way to deal with that? Well, we would integrate it, right? So we integrate it. And so now IL should equal 1 over L integral Vn dt. Oh, that's good. Oh, I should make that capital. Sorry. Well, oh, wait a second. My nodal equation was IL IR. Now, rather than Vn minus Vx divided by something, hey, wait, no, I've got an equation right there. Oh, that's sweet. So 1 over R integral of Vn dt. If we recall, that was Vx minus V out. Oh, I'm getting ahead of myself. That's a L, right? The Vx was 0. So it was minus V out over R. And so now solve for V out of T equals minus R over L. dt. So what I found is that when there's an inductor or a capacitor and I can't use the Laplace transform because I've forgotten it or something, I got to use nodal. But let's just say nodal method 2, right? V plus equals V minus because negative feedback, AV is infinity. All right. But notice there was another trick here. Like so many times we do a nodal analysis and then we put in a voltage minus another voltage divided by a resistance. Voltage minus a voltage divided by a resistance. But in this case, we couldn't do it that way. But in a way, it was even easier because we had an equation for the current directly, right? Which leads us to a whole other series of problems or solutions, because these are circuits that have a solution. So when I first saw this, I was like, what? But where's that current coming from? Well, if you have a diode and you shine light on it, okay? So diodes have curves that can kind of look like this with light. The more light, the more current you get. And there, you know, if it's a photodetector. So I've just called it a current source, right? But it's really a reverse bias diode and all of that. Well, I can't necessarily, I'm like, well, there's an R, but then there's not an R over here. It doesn't look like anything I've ever seen before, but it's ideal. And notice, R is providing feedback from out to V minus and V plus, right? R provides feedback. So V minus equals V plus. Now in this case, it just equals to each other. We don't really know. It's not tied to anything. But notice, I'm going to call this 2 and R1. VR2 equals IN times R2, right? Because the current can only go this way, right? It can't go that way. And VR1 equals IN, right? Because this is current's going this way, and I'm defining it like that. The current would be going this way, and I'm defining that drop like that. And so VR1 equals IN times R2. And then you'd actually, it doesn't look like a mesh problem, does it? But look, I have VR2 plus minus. I have, I'm just going to, it's a weird name, but I'm going to call it VIN plus minus. And then I have another voltage plus VR1, right? And that goes, so all of that sums to V out, right? So V out equals VR1 plus VIN plus VR2, but V plus equals V minus, so VIN equals 0. Oh, now V out equals VR2 plus VR1 equals IN R1 plus R2. And so this current source, right, which is from a photodetector bouncing light, right? So if I have a flashlight and I'm getting closer to something, this circuit is converting that current from that flashlight into the output voltage, right? And that output voltage, right, could then be fed back into our comparator circuit, right? Which then could be used, you know, to turn the LED on that somebody's getting too close. Somebody with a flashlight is too close. You need to back off or something. Okay. So in a sense, we hit almost every problem that you would see on the 101 exam. But not only that, you could almost pass, I think, an internship interview with just what we covered today. But when you're on the interview, just to give you a hint, right? Let's say you see this circuit. Don't start writing equations. They want to see you puzzle it out live. Even if you're wrong, it's better to be right though, right? But just don't all of a sudden drop your eyes and start writing, right? It's better to think it out loud. Even if, yeah, you have to practice that in front of the mirror or something. Any questions before I let you go? All right, well, here's the thing. All right, so the question is shining a light in an LED? Well, LEDs emit light, but if you shine light on them, it will generate current. All diodes can be LEDs or photodetectors. They just might be really bad at it. Okay, so silicon does not emit like a statistically significant amount of light, but it can act like a solar cell. It can act like a photodetector. Okay. Alrighty. I guess let's see.